All right, so for this example, we're going to be comparing the difference between the instantaneous and the average rate of change for the function x squared. So I'm just going to throw up the graph of x squared right quick. And we are asked first for the average. And we're doing the average between or from 0 to 4. And so this is for x equal to 0 to x equal to 4. So we're going to go from this point right here all the way up to 4. And if we go up to 4, that should give us a value of 16. So way up here. All right, cool. So we're going from here to here, and if we're doing the average rate of change, then the function we're going to be using doesn't really even involve calculus. We're just going back to algebra, and we're going to be doing f of x2 minus f of x1 over x2 minus x1, which in this case is going to be the function evaluated at 4 minus the function evaluated at 0 over 4 minus 0. If I go ahead and do that, f of 4, since it's x squared, that's going to be 16. 16 minus 0 over 4 minus 0. We're going to get 16 over 4, which is 4. So the average rate of change between these is 4, and so I can represent that with a line of slope 4. So, like that. So notice that this line does not actually touch the graph except for these 2 points right here. And that's why it's just the average rate of change, right? Not the instantaneous. Because the actual slope or rate of change, if you look here, is different along the actual curve. It varies. It looks like about here it matches that, but then it starts getting more steep over here. So all the, it's not negative, but less steep slopes here sort of get canceled out by the more steep slopes up here, and so we get this average right here. Now, what if we wanted the instantaneous? Well, that's also what the question asks for. And so if I do the instantaneous rate of change, what's interesting here is that when I did the average, I needed 2 points. I had to do the 0.00 and the 0.416. For instantaneous rate of change, I actually need only 1 point. So if you have these 2 points, you might get different instantaneous rates of change at these 2 points. So the problem does have to tell you what point to use. I'm just going to go ahead and compare them. So I'll go ahead and take the derivative. That's the instantaneous rate of change. So that's just going to be 2x for this function. And now if I check what the instantaneous rate of change is at 0, I just get 0. So that's just a flat line. It's the rate of change down there. And if I check what the instantaneous rate of change is at 4, well, I get 2 times 4 is 8. And so that would be a slope of 8. And again, notice that's way steeper than the average rate of change graph right there. We could also check it at another point. We could check it at the point 2. Let's just go ahead and do that. I'm just picking that arbitrarily. So 2 on the graph is like right here. And so f prime of 2, 2 times 2 is 4. Oh, look at that. That matches our average rate of change. And I made a comment earlier that at some of these points, it lines up a little bit. So I'm not the best artist in the world, but it's actually at this point that we're lining up with our average rate of change. But notice it's only at that point. As soon as I plug in other things, 2 times anything else besides 2 is not going to equal 4. And so this is the only place where the instantaneous rate of change actually equals the average rate of change between 0 and 4. So again, that's the main difference. Remember that for average rate of change, you don't even really need calculus. You're just doing algebra, evaluating the slope right here. When you do instantaneous, that's where the calculus comes in, and you don't need you don't need 2 or more points. You just need 1. And I just plugged in several points so we could compare the different instantaneous rates of change. So that is this example.